Howdy. This video is on how to build Lewis electron dot diagrams. Lewis diagrams are simple yet powerful tools for helping us understand where valence electrons are in the molecules. As long as you're doing chemistry, you will be doing Lewis electron dot diagrams. Lewis diagrams are two-dimensional, and so they do not accurately depict the three-dimensional structure of molecules. After watching this video, you should be able to determine Lewis electron dot diagram given a chemical formula. You should be able to determine all the bond orders of a molecule using Lewis electron dot diagram. You should be able to put a series of bonds in order of increasing bond strength using Lewis electron dot diagrams and bond orders. Lewis diagrams help keep track of the valence electrons around atoms, ions, and molecules. It's just about the valence electrons. If you know the number of valence electrons, drawing Lewis diagrams is not too hard. Lewis diagrams is primarily used for S and P block. So the S block are composed of the two columns on the left-hand side of the periodic table. The P block corresponds to 6 columns on the right-hand side of the periodic table. But it is essential that you learn how to draw Lewis diagrams. For atom, the Lewis diagram is really pretty straightforward. It just kind of illustrates the valence electron configuration. And so for oxygen, we have the valence shell is the second shell. And so we have a pair in the 2s orbital, which corresponds to a pair of dots next to the oxygen. You got a pair in one of the 2p's, which corresponds to another pair of dots. And then you got single electrons in the remaining 2p orbitals, which correspond to single dots. And so a pair of dots represents a pair of electrons sharing an orbital. A single dot represents an electron alone in the orbital. And so it's kind of cool. The Lewis diagram gives you information about the valence electron configuration. Now it doesn't matter which side you put the dots, as long as you have 2 pairs and 2 single dots for oxygen. You know, we can look at the 3 rows of the periodic table, and again in the column, elements have the same valence electron configuration, and so their Lewis diagrams look very similar. And so we have different models for atoms. We have the Lewis diagram, we have the Bohr model, which shows you the different shells. We had the atomic orbitals, the S and P, 1s, 2s, and 2p. In actuality, if we're able to look at an atom by itself, it would just look like a fuzzy ball. The orbitals would be in a superposition, and so it's kind of interesting. In some cases, you know, Lewis diagram is a much better model, more helpful model than the Bohr. We can use the Lewis diagrams to try to understand how ionic compounds form. You know, if we start with a sodium atom and a chlorine atom, the sodium atom will lose an electron, becoming a sodium ion. The chlorine will gain that electron, become the chloride ion. And then in the ionic solid, these ions will be packed next to each other, and the ionic solid is formed because of the ion-ion interaction, because of that electrostatic attraction between the ions. Molecular compounds are formed when nonmetal atoms share electrons. And so each fluorine atom starts with 7 valence electrons. And then if they form a bond, if they share 2 electrons, now each atom will see 8. And so often we say that elements tend to gain, lose, or share electrons to get noble gas configuration. By sharing those 2 electrons, each fluorine sees 8 valence electrons. Each fluorine has noble gas configuration. Now the electrons being shared are referred to as the bonding electrons. And the electrons not shared, those are the unshared electron pairs or lone pairs. And it's very important that when you're doing Lewis diagrams, you make sure you use the right number of valence electrons. So each fluorine atom starts with 7. 2 times 7 gives us 14. And so we have to use 14 valence electrons for the fluorine molecule. Now typically for the bonding electrons, we'll just draw a line. And so each line corresponds to 2 electrons, a pair of electrons. Now the bond order, remember for a single bond, bond order is 1. For a double bond, bond order is 2. For a triple bond, bond order is 3. We could ask what's the bond order for the oxygen-oxygen bond in O2. And so when you're doing Lewis diagrams, often trial and error is needed. And so what we could do well, first we have to do is count the number of valence electrons. And so each oxygen has 6. 2 times 6 is 12, so we have 12 valence electrons. We could try drawing a single bond, and then we have 10 electrons left, and so 2, 4, 6, 8, 10. We used a total of 12 electrons. Now if we look at this oxygen is surrounded by 2, 4, 6, 7, so neither oxygen has noble gas configuration. And so we didn't have enough valence electrons to get everything noble gas configuration with a single bond. And so what we can do is we can try a double bond. Now with a double bond, now this oxygen sees 2, 4, 6, 8. This oxygen sees 2, 4, 6, 8. So both have noble gas configuration. We used 2, 4, 6, 8, 10, 12. We used 12. And so that should be a relatively stable structure. Now we have a double bond there, and so that means the oxygen-oxygen bond should have a bond order of 2 in the oxygen molecule. We asked a similar question about the bond order of nitrogen-nitrogen bond in N2. And so first we have to count the number of valence electrons. So each nitrogen atom has 5. 2 times 5 gives us 10. Now we could try single bond. And so 2, 4, 6, 8, 10. We use 10 electrons. Now, if we look at how many electrons surrounding this nitrogen, 2, 4, 6, only 6. And so that's not going to be a stable structure. Typically what we're trying to do is get noble gas configuration. We could try a double bond. And now what we see is 2, 4, 6, 7. 7 electrons around that nitrogen. Still not noble gas configuration, so it's still not stable. Now if we try a triple bond, 2, 4, 6, 8. So that nitrogen sees 8. This nitrogen sees 2, 4, 6, 8. So both nitrogens have a noble gas configuration. And again, elements tend to react by losing, gaining, or sharing electrons to get noble gas configuration. And we used 2, 4, 6, 8. We used 10 electrons. We started with 10 valence electrons. You always have to use the number of valence electrons that you started with. And so the bond order for the nitrogen-nitrogen bond is 3. And so we could ask, which of the following has the strongest bond for an oxygen and nitrogen? Now, the larger the bond order, the stronger the bond. And so the nitrogen has a bond order of 3. It's got that triple bond. And so of these 3, N2 should have the strongest bond. It also has the shortest bond. Remember, the more electrons you have between the nuclei, the closer the nuclei can get. The bond energy is 932 compared to 44 compared to 146. Remember, each line here represents 2 electrons, and so the nitrogen atoms are sharing 6 electrons. The oxygen atoms are sharing 4, and the fluorine atoms are sharing 2. So the greater the bond order, the more stable, the shorter the bond, the stronger the bond. And again, single bonds have a bond order of 1, double bonds have a bond order of 2, and triple bonds have a bond order of 3. Now, we looked at for diatomic molecules. And for diatomic molecules, you can just try and see what happens and try an error. For a little bit more complex molecules, you may want to be a little bit more systematic. And so there's 4 steps to drawing Lewis diagrams. The first step is you count the number of valence electrons. And so hydrogen atoms have 1, nitrogen atoms have 5. We have 3 hydrogens, so 3 times 1, plus the 5 from the nitrogen, and so that gives us 8 valence electrons. And then the second step is to predict an arrangement of the atoms. Now, because hydrogen can only have a single bond, that means nitrogen must be the central atom. And so we can draw it this way. Now we used 2, 4, 6 electrons. We have 8, and so we can end up putting the last 2 on top of the nitrogen. Now the hydrogen sees 2, which for it is noble gas configuration of helium. The nitrogen sees 2, 4, 6, 8, and so that's also noble gas configuration. And so all 4 of these atoms have noble gas configuration, and so that should be a stable Lewis diagram. Now please remember, when you're doing Lewis diagrams, you basically rip the valence electrons off the atoms, and then you put put them around the atoms to make the most stable structure. You don't have to worry about where the valence electron started with. And again, trial and error is often needed. And also, Lewis diagrams are two-dimensional, molecules are three-dimensional, so Lewis diagrams do not actually represent the structure of the molecule. And so this is our Lewis diagram for ammonia. To the right is a good depiction of the structure of the molecule. The bond angles there are about 109 degrees, about 107 degrees if I remember right. And it's kind of cool. You see that lone pair, and that also corresponds to the red part here. Remember, the red has a partial negative charge. The blue is a partial positive charge. We can try another example for here. Here we have water. And so, again, hydrogen has 1 valence, oxygen has 6. We got 2 hydrogen. So 2 plus 6 gives us 8 valence electrons. Now, again, hydrogen can only have a single bond. And so we'll assume oxygen is the central atom. And so we can start with single bonds. And that uses 2 4 valence electrons. There's 4 left, and so we can put those on the oxygen. Typically, they go on the center atom. Now, hydrogen, the noble gas configuration of helium, and so it has 2 electrons. Hydrogen will only ever have a single bond. Oxygen sees 2 4 6 8, so it also has noble gas configuration. And again, valence electrons do not have to stay with the atom that they start with. And again, often trial and error is needed. So just try, if you're not sure what to do, just try something, and then you can always improve upon it. And again, Lewis diagrams are two-dimensional, and so they do not accurately depict the actual structure. And so on the left we have the Lewis diagram for water. On the right we have a pretty good depiction of the water molecule. Remember, molecules are kind of globby-like. The bond angle for the hydrogen-oxygen bond angle is about 105 degrees. We can try the carbonate ion, and so CO3 2-. And so carbon has 4 valence electrons, oxygen has 6. And that 2- charge means you have 2 extra electrons. And so 3 times 6 is 18, plus 2 gives us 20, plus that 4, so we have 24 valence electrons that we have to use. Now, we could assume that the carbon is the center atom. That should be a decent assumption. And so if we start with just single bonds, so I used 24 valence electrons, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Now the oxygen should be happy. Each oxygen sees 8, which is noble gas configuration, but the carbon only sees 2, 4, 6. And so the carbon doesn't see a noble gas configuration. And so if you don't have enough electrons to give everything a noble gas configuration, you can try double or triple bond. And so if we take this pair of electrons and make a double bond here, like this, now each oxygen again sees 8, 2, 4, 6, 8. So each oxygen still is happy with noble gas. Now the carbon sees 2, 4, 6, 8. Carbon also sees noble gas configuration. And so if you're not sure what to do, just try something. If you don't get it right, then you change it. Remember, trial and error is often needed. Now, for the carbonate ion, you have 3 regions, and we'll see later that corresponds to trigonoplanar electron geometry. And so the Lewis diagram is just 2-dimensional nature. The molecules are 3-dimensional nature. On the right is a decent depiction of what it looks like. And we'll talk about this a little bit more later. Each of these carbon-oxygen bonds should be exactly the same. And so you actually have what's referred to as resonance structures. The double bond could be here, there, or there. But again, it's kind of confusing. We draw it this way, and it looks like the hydrogen-carbon-hydrogen bond angle should be 90 degrees, but in actuality, it is 107.5 degrees. So again, please remember, Lewis diagrams are just 2-dimensional nature, and so cannot accurately depict the structure of molecules. So hopefully you can draw Lewis diagrams given chemical formula. You should be able to determine bond orders of all the bonds, again using Lewis electron dot diagrams, and you should be able to put molecules in order of increasing bond order by first drawing the Lewis diagrams and then looking at the bond orders. I hope that was helpful.